Look up at the night sky for a moment. Those tiny points of light, some of them are so far away that their light began traveling toward us before humans even existed. And yet somehow we know how far away they are. Think about that. No one has traveled to those stars. No one has stretched a measuring tape across space. No spacecraft has reached the edge of a distant galaxy. So how do we measure something that we cannot touch, cannot visit, cannot even fully imagine? This is one of the quiet triumphs of human thinking. With nothing but light, geometry, and careful reasoning, we have learned to measure the universe, not by guessing, not by believing, but by observing and thinking clearly. Today, we're going to explore how we measure distance in space, step by step, the way a curious mind would approach it. Slowly, logically, honestly. Let's begin. Let's begin with something close, something we can almost feel. The moon. It hangs above us at night, quiet, steady, familiar. But how far away is it really? It looks close, but looks can be deceiving. The average distance to the moon is about 384,000 kilometers. That's far enough to fit all the planets of our solar system in between Earth and the moon side by side. So how do we measure that distance? We don't guess, we don't estimate by eye, we measure it with light. Here is the idea: simple, powerful, precise. Light travels at a known speed, about 300,000 kilometers per second. Not approximately, not vaguely, exactly defined by physics. So if you send a pulse of light somewhere and it comes back, you can measure how long the journey took. Time, speed, distance. But there's one detail. The light travels to the moon and then back, so we divide by 2. Distance equals speed of light multiplied by time divided by 2. That's it. And this is not theory, we actually do this. During the Apollo missions, astronauts placed special mirrors on the surface of the moon. They're still there. From Earth, scientists fire powerful laser pulses at those mirrors. Most of the light scatters, but a tiny fraction reflects back. Sensitive detectors measure the returning pulse. The entire round trip takes about 2.5 seconds. And from that small interval of time, we calculate the distance with astonishing precision. Not kilometers, not meters, centimeters. Think about that. We are measuring the distance to another world by timing a flash of light to a fraction of a second. No guesswork, no assumption, just time, light, and logic. This works beautifully for nearby objects. We use similar techniques to measure distances to planets. We send radio waves to Venus or Mars, they bounce back. We measure the delay. It's elegant, direct, reliable. But now pause. Notice something important. This method depends on something coming back. A reflection, an echo. And that only works when the object is close enough for us to send a signal there and receive it again. What about a star? The nearest star beyond the sun is more than 4 light years away. If we sent a signal there today, we wouldn't get a reply for over 8 years. And that assumes it could even reflect anything back. So here's the turning point. For nearby objects, we measure distance by timing light. But the universe is much bigger than our neighborhood, much bigger. So the real question becomes, if we can't send a signal and wait for it to return, how do we measure something that never sends anything back? That's where things become more subtle and far more interesting. Let's go deeper. Now let's go a little farther than the moon, far enough that sending a signal and waiting for it to return is no longer practical. We need a quieter method, a method that doesn't require touching the star, only observing it. Hold your finger out in front of your face. Close your left eye. Now switch to your right. Your finger appears to shift against the background. It didn't move. You did. That small apparent shift is called parallax. It happens because your 2 eyes see the world from slightly different positions. 2 viewpoints create a tiny angle. That angle reveals distance. Now imagine something much larger. Instead of your 2 eyes separated by a few centimeters, use Earth's orbit around the sun. In January, Earth is on one side of the sun. 6 months later, it's on the opposite side. That's a separation of about 300 million kilometers. We observe a nearby star in January. Then we observe it again in July. Against the distant background stars, the nearby star appears to shift just a little, almost imperceptibly, but measurable. And once we measure that tiny angle, geometry does the rest. No brightness assumptions, no complex physics, just a triangle drawn across space. Large shift, the star is close. Small shift, the star is far. Simple, quiet, precise. But here's the limit. As stars get farther away, the angle becomes smaller and smaller and smaller and smaller, until eventually it becomes almost impossible to detect. And that's when we must ask, If geometry can only take us so far, how do we measure distances? When even the triangle disappears. Now geometry has taken us as far as it can. The triangle becomes too thin, the angle too small, the shift disappears. So what do? We change the question. Instead of asking, how much did it move? We ask, how bright is it really? Imagine you see a light bulb far away in the dark. If you know how powerful that bulb truly is, how much light it actually produces, then how bright it appears to you tells you the distance. Bright appearance, it's close. Dim appearance, it's far. Not magic, just the way light spreads out. Light doesn't travel in a tight beam. It spreads like ripples in water. The farther it goes, the more it thins out. So if something looks faint, it may not be weak. It may simply be far away. Now here's the clever part. The universe gives us certain stars that act like standard light bulbs. One famous example is the Cepheid variable star. These stars don't shine steadily. They pulse. Bright, dim. And here is the key discovery. The rate at which they pulse is directly related to how bright they truly are. Slow pulse, very luminous. Fast pulse, less luminous. So by measuring the rhythm of the pulse, we know the star's real brightness. Then we compare that to how bright it appears from Earth, and from that comparison distance emerges. No guesswork, no speculation, just light behaving honestly. It's like hearing someone shout in the dark. If you know how loud their voice really is, the softness of the sound tells you how far away they stand. With this method, we reach far beyond nearby stars, beyond our neighborhood, into distant regions of our galaxy. But even this has limits, because eventually even these stars become too faint to see. And then, once again, we must climb higher on the cosmic ladder. Just light behaving honestly. It's like hearing someone shout in the dark. If you know how loud their voice really is, the softness of the sound tells you how far away they stand. With this method, we reach far beyond nearby stars, beyond our neighborhood, into distant regions of our galaxy. But even this has limits, because eventually even these stars become too faint to see. And then once again we must climb higher on the cosmic ladder. Now let's go bigger. Not stars, not even clusters of stars, galaxies, entire cities of stars, millions, billions of them drifting in the dark. When astronomers began studying distant galaxies in the early 20th century, something strange appeared. The light from those galaxies was shifted, not randomly, not slightly, systematically, shifted toward red. This effect is called redshift, and it was carefully measured by astronomers like Edwin Hubble. Here is what redshift means. Light is a wave, and waves can stretch. If something moves away from you, the waves it emits get stretched out. For sound, that means lower pitch. For light, that means redder color. Like an ambulance siren dropping in tone as it drives away. But galaxies aren't just moving through space. Space itself is expanding. Imagine dots drawn on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. Not because they are running, but because the surface itself is stretching. That's our universe. The farther a galaxy is from us, the faster space stretches between us. Just light behaving honestly. It's like hearing someone shout in the dark. If you know how loud their voice really is, the softness of the sound tells you how far away they stand. With this method, we reach far beyond nearby stars, beyond our neighborhood, into distant regions of our galaxy. But even this has limits, because eventually, even these stars become too faint to see. And then once again we must climb higher on the cosmic ladder. And the faster it stretches, the more its light is stretched. So here is the key idea. Measure how red the light is, and you measure how fast the galaxy is receding. Measure how fast it's receding, and you can calculate how far away it must be. Distance from motion, motion from stretched light. No ruler, no triangle. Just a quiet fingerprint of expansion. And suddenly, we're not measuring thousands of kilometers, not even light years. We're measuring millions, billions of light years. But now a deeper question begins to form. If space is expanding, if everything is moving away from everything else, what does that say about the beginning? And where exactly is this expansion taking us? Now, step back for a moment. What are we really doing here? We have never touched a star. We have never traveled to a distant galaxy. We have never stretched a ruler across space. And yet we measure the universe. How? We measure tiny angles in the sky. We measure how light fades with distance. We measure how long light takes to travel. We measure how light stretches as space expands. Angles, brightness, time, color, simple things, and from those simple measurements distance appears. Not because we guessed, not because we believed, but because nature behaves consistently. This is the quiet power of physics. You don't need to visit a star to know how far away it is. You just need to observe carefully and think honestly. Each method we use, laser reflections, parallax, standard candles, redshift, they are not separate tricks. They are steps, a ladder, each step tested, checked against the others, refined over decades. And slowly, patiently, the scale of the universe revealed itself. This is the big idea. The universe is not beyond understanding. It does not hide behind mystery. It leaves clues. Light carries information. Geometry whispers structure. Motion reveals history. And our job is simply to listen carefully, not to force answers, but to follow the evidence wherever it leads. And when you realize that we can measure billions of light years using nothing but light and logic, you begin to see something extraordinary. The universe may be vast, but it is not unreachable, because the laws that govern distant galaxies are the same laws that govern the light entering your eyes right now. That's our universe. The farther a galaxy is from us, the faster space stretches between us. Just light behaving honestly. It's like hearing someone shout in the dark. If you know how loud their voice really is, the softness of the sound tells you how far away they stand. With this method, we reach far beyond nearby stars, beyond our neighborhood, into distant regions of our galaxy. But even this has limits, because eventually, even these stars become too faint to see. And then once again, we must climb higher on the cosmic ladder. So the next time you look up at the night sky, pause for a moment. Every star you see, every distant galaxy, we have measured its distance using nothing but light, geometry, and careful thought. No guessing, no magic, just curiosity, just observation, just the quiet power of thinking clearly. And that is the true wonder of the universe.